Alright, in the last video we have learned three types of algorithm runtime notations such as big O, big omega, and big eta. Now in this video we will look at some examples of runtime complexities. There are many time complexities exist in the world of algorithms, but here we will look at the most commonly used complexities. Here's the list of complexities that we are going to discuss. So the first one is O1, which is also called an order of 1 or constant time complexity. This means that for any given input, the execution time will not change. It will remain constant. As an example, accessing a specific index within the array always takes O1 time complexity. It doesn't matter whether the array has 10 or 100 indices, looking up for a specific location of array will take the same amount of time. Therefore, the function has constant time lookup. In much the same way, if I had a deck of cards and I ask you to remove the first any card at random, you could simply grab a card from the deck without having searched through the entire deck. So this is very easy task, and this takes constant time, whatever card we grab. So this is called constant time complexity. Now the next time complexity that we are going to learn is ON time complexity, which is also called linear time complexity. Here, the time complexity will grow in direct proportion of size of the input data. The best practice is to try to keep our functions running below or within the range of time complexity, but obviously it won't be always possible. A good example for linear time complexity is looping through array elements. So here we have a sample Java code in which we are looping through this array over here. So as you can see, lookup is directly related to size of our input because we will be going through each item within the array. In other words, the larger input, the larger amount of time it takes to perform function. Of course, if the array had only one element, the function will have a constant time lookup. Now in this case, we have 5 elements in our array, so the time complexity will be O5, but if we have 1 million elements, it's going to be O1 million. So it depends on the number of elements in our array. Now, if we go back to our deck of cards analogy, so if I had a deck of cards like this, and I want you to select a specific card, let's say 10 hearts. So you will have to look through every card until you find that card. Sure, there's a possibility that it will be first card in the deck, but this is highly unlikely. Now think about if the deck of cards were filled hundreds of other non-10 heart cards. Your search is directly related how large the deck of cards is. So in this case, this is an example of linear complexity. Now the next time complexity is logarithmic time complexity, which is also called log n time complexity. This complexity refers to the algorithm that runs in proportionally to the logarithmic of the input size. So if you look at this code over here, we are logging numbers until the array length is reached. However, we see that in our function, we are logging numbers at a certain interval. It should be also noted that since our function does not pass through all index of array, it will not be linear time. By using the loop over here, we start from the first element, which is the index of 0, and we loop until we reach the length of array. But here, we are visiting every third element, not all of them. So that's why the time complexity in this case is going to be logarithmic time complexity. Now using our deck of cards analogy, let's say our cards are ordered and split it into two parts. In the first part we have diamonds and clubs, and in the second part we have hearts and spades. So if we are going to pull out 10 hearts, so you could safely conclude that the cards should be in the second pile. So we can remove the first pile from here. So we are taking on the second part, so we know that the cards should be in the hearts row. So this means that we can exclude this row from here, the last row. So we will look at only this row over here. Now here we will select the middle one, so the middle element is 7. So we will compare 7 with 10, which is the element that we are looking for. So we will see that 7 is less than 10. So this means that we can exclude these elements from here, take the elements that are greater than the 10. So in this case, one more time we will divide into 2 and we can see that 10 is middle element and we can select the 10 from here. So in this case, as you see, we are not looping through all elements of these cards over here. We are only looping the certain level of elements. So that's why the time complexity in this case, logarithmic time complexity. So another example for logarithmic time complexity can be binary search. So if you don't know binary search, I'm going to explain it in searching algorithms, but here you just need to know that by using binary search, we are searching for an element in a sorted array. So in this case, we have an array like this, so we are searching for 9. So the first thing that we are going to do, we need to find the middle. So the middle of this array is 11. So we will compare 11 with 9. We will see that 9 is less than 11. So this means that we can remove all elements that are bigger than 11 from this array. So in this case, our array becomes like this. So one more time here, we will compare the 9 with the middle elements. In this case, the middle element is 8. So we see that 9 is greater than 8. So we will take the elements that are located on the right of 8. So we are taking this one. So in the next stage, we see that 9 is equal to 9. So this means that, so we have found the number that we are looking for. Now in this case, you see that in each case, we are dividing the number of elements by 2. So that's why it takes logarithmic time complexity, because we are not searching through all elements of the array over here. So this can be expressed like this. So 2 to the power of k is equal to n. So this means that in what power of 2 we can find n. So for example, if n is 16, so we know that 2 to the power of 4 will be 16. So this means that in 4 steps we can find this element. So this is logarithmic time complexity. Now the next time complexity is quadratic time complexity. Quadratic time complexity represents an algorithm whose performance is directly proportional to the squared size of input dataset. You can think of it as a linear, but it is squared. Within our programs, this complexity will occur whenever we nest over multiple iterations within the dataset. Now here, from this example, you can see that we have 2 loops inside each other. So this means that this will take quadratic time complexity because when I equals to 0, we are looping through all elements of the array one more time. Then it continues. When it is 1, then we are looping all elements of the array. So this is repetitive until all elements are reached. So this means that this is quadratic time complexity. So to make things clear, let's revisit our deck of cards. Let's say you pick the first card in the deck, which is 3 club in our case. And to get all cards with the same number, we need to search through the deck and getting the duplicates at every point. So once you are sure that you got all duplicates, then we continue to do the same thing for the second card, then the third card, and until we reach the end of deck. So this is an example of quadratic time complexity. Now the last one that we are going to explain over here is exponential time complexity. Exponential time complexity denotes an algorithm whose growth doubles within each addition to the input side. So as the input increases, the growth rate doubles itself. So if you know other exponential growth patterns, this works in much same way. The time complexity starts off very shallow and rising at every increasing rate until the end. So in this case, we have created a recursive function for Fibonacci numbers. So this is a great way to express exponential time complexity. Although there is a way to make Fibonacci function have a short time complexity, but for this case, we are using double recursive method over here to show that this will be the exponential time complexity. In a few words, the recursive instantation will pass over every number from the number to 0. It will do this twice until it reaches the base case if statement. So the base case if statement says that if n equals to 0 or if n equals to 1. So since the number of recursive call is directly related to number of input, it's easy to see how this time complexity will quickly grow out of n. Now here in this lecture, we have explained most commonly used complexities, and it's normal that you might not understand some terms in this lecture. You don't need to worry about this, we will cover them in detail in our upcoming lectures. So you might be interested why we are including such concepts here. So the answer is without these concepts, we cannot explain different types of complexities. Now let's see how the time complexities are depicted in the graph and which ones are good for faster and efficient program. Now here in the x-axis, we have a number of input elements, and on the y-axis, we have operations. As we mentioned before, the best practice time complexities are below ON. So you can see from this graph that below ON, we have green color. So this means that O log n and O1 are the best time complexities. So when we go up, you see that the color changed to yellow. This is average case. Now, if we continue to go up, you see that it becomes orange. So this becomes worse. So ON log n time complexity becomes worse. But this red part over here is horrible time complexities. This means that as the input increase, the time complexity will go high and high. So this part of time complexities over here are horrible time complexities. So we need to avoid these time complexities in our program to make efficient program. So with this, We have come to the end of this video, so hopefully you have understood the differences between time complexities and you have an idea of which one is desirable. So see you in the next lecture.